Ohm's law is a fundamental principle in the world of electricity and electronics. It provides the basic framework for understanding how electrical circuits operate. At its core, Ohm's law helps us grasp the essential relationship between the key elements within any electrical circuit. This understanding is crucial for both analysis and design. This law precisely describes how voltage, current, and resistance interact with each other. It is truly a cornerstone of all electronics, guiding how we build and troubleshoot devices. Ohm's law is named after the pioneering German physicist Georg Simon Ohm. He published his groundbreaking findings on these electrical relationships in the year 1827. The law itself is expressed as a simple mathematical equation. This equation clearly demonstrates how electrical current flows through any conductive material. To fully understand Ohm's law, we first need to get to know its three main components. These are the key players in any electrical circuit. The three fundamental quantities we will explore are voltage, current, and resistance. Each plays a distinct role in how electricity behaves. These three quantities are deeply interdependent within any circuit. A change in one will directly influence the others, always according to Ohm's law. First, we have voltage, often represented by the letter V. It is the push or pressure that drives electric charge through a circuit, also known as electric potential difference. Voltage is measured in units called volts. Next is current, represented by the letter I. This is the actual flow of electric charge, specifically electrons, through a conductor. Current measures the amount of charge moving past a point per unit of time, and its unit is amperes, often shortened to amps. Finally, we have resistance, denoted by the letter R. Resistance is simply the opposition to the flow of electric current. It describes how much a material resists the movement of electrons, and it is measured in ohms. Now that we understand the three key players, let's look at the core of Ohm's law, its mathematical formula. This equation brings together voltage, current, and resistance. This formula precisely connects voltage, current, and resistance in a simple, elegant way. It allows us to calculate any one of these values if we know the other two. The primary form of Ohm's law states that voltage equals current multiplied by resistance. This is often written as the letter V equals the letter I times the letter R. This equation shows that voltage is directly proportional to current, meaning if one increases, the other increases. Voltage is also directly proportional to resistance. However, current is inversely proportional to resistance for a constant voltage, so if resistance goes up, current goes down. The triangle helps you quickly recall how to rearrange the formula. It's a handy trick for solving circuit problems on the fly. To find the voltage, you would multiply the current by the resistance. So, voltage equals current times resistance. If you need to calculate the current, you divide the voltage by the resistance. This means current equals voltage divided by resistance. And to determine the resistance, you divide the voltage by the current. Therefore, resistance equals voltage divided by current. To make these abstract concepts more concrete, let's use a common analogy. Imagine electricity flowing through a wire like water moving through a pipe. This water pipe analogy helps us visualize the otherwise invisible flow of electrical energy. It makes the relationships between voltage, current, and resistance much easier to understand. In this analogy, we can picture electricity flowing through a wire just like water travels through a pipe. Each electrical quantity has a direct parallel in the water system. Voltage is comparable to the water pressure in the pipe. A higher voltage is like having more pressure, which creates a stronger push for the water, or electrons, to move. Current, in this analogy, is like the water flow rate. It represents how much water is actually moving through the pipe at any given moment. A greater current means more charge is flowing. Resistance is similar to the narrowness or any obstruction within the pipe. A narrower pipe or an obstacle creates higher resistance, which restricts the water flow, just as higher electrical resistance limits current. Imagine a simple water pump system. The pump pushes water through a pipe, which has a narrow section in the middle. In this analogy, the strength of the pump is like voltage in an electrical circuit. The flow of water through the pipe represents the current, which is the flow of electrical charge. The narrow section of the pipe, which restricts water flow, is analogous to resistance in an electrical circuit. Now let's put Ohm's law into practice with a simple circuit example. we'll see how to apply the formula to real-world scenarios. Ohm's law is incredibly useful for calculating unknown values in a circuit. If you have two of the three quantities, you can always find the third. First, let's establish the basic circuit, represented by these connecting wires. Next, we add the key components, a voltage source, like a battery, and a resistor, which impedes current flow. This arrow indicates the direction of conventional current flow through the circuit. Finally, we label the components, V for voltage, I for current, and R for resistance, representing the fundamental quantities in this circuit. Let's consider a practical example, a simple circuit powered by a battery, with a light bulb acting as our resistor. This setup allows us to apply Ohm's law directly. A key takeaway from Ohm's law is that if we know any two of the three values, voltage, current, or resistance, we can always calculate the third unknown value. Let's work through an example problem to illustrate how Ohm's law is applied. This will help solidify your understanding. In our example, we are given that the voltage is 12 volts. We also know that the resistance in the circuit is 4 ohms. With these two known values, our task is to determine the amount of current flowing through this circuit. What is the current in amperes? Now, let's systematically solve this problem using Ohm's law. We'll break it down into clear, manageable steps. We'll follow a step-by-step calculation to find the unknown current. This structured approach ensures accuracy and clarity. The first step is always to clearly identify what values are known and what value needs to be found. This helps organize our thoughts. In this problem, our known values are a voltage of 12 volts and a resistance of 4 ohms. The unknown quantity we need to calculate is the current. The second step involves selecting the appropriate formula from Ohm's law that allows us to solve for the unknown current. We need the equation that isolates current. The correct formula to find current is voltage divided by resistance. So, the letter I equals the letter V divided by the letter R. Our third step is to substitute the known numerical values into our chosen formula. This prepares the equation for calculation. So, current equals 12 volts divided by 4 ohms. We are now ready to perform the final calculation. Finally, we calculate the result of our substitution. This gives us the answer for the current flowing through the circuit. The calculation yields a current of 3 amperes. This is the amount of electrical charge flowing through our example circuit. Therefore, a current of 3 amperes will flow through the circuit when a 12-volt battery is connected to a 4-ohm resistor. Let's summarize the key takeaways and the dynamic relationships within Ohm's law. This highlights its practical significance. Understanding how changes in one quantity affect the others is vital for circuit analysis. Ohm's law provides these crucial insights. Ohm's law fundamentally links voltage, current, and resistance, showing their direct interdependence. It is absolutely crucial for designing and troubleshooting all kinds of electronic circuits. If the voltage in a circuit increases and the resistance remains constant, then the current will also increase. This demonstrates their direct proportionality. Conversely, if the resistance increases while the voltage stays constant, the current will decrease. This illustrates the inverse proportionality between current and resistance. Ohm's law has countless real-world applications across various fields of electrical engineering. It's a foundational tool for many practical tasks. Applications include correctly sizing resistors for components like light-emitting diodes, calculating the power consumption of electrical devices, and designing essential safety features like fuses and circuit breakers. It also helps us understand how different materials conduct electricity.